Well, first of all, I'd like to thank everybody and thank the organizers for inviting me. I made the title up a couple of weeks ago, and then when I was preparing the talk, it's more like mixed motives associated to curves of higher genus, but it's really an application of the elliptic case. And the truth is that I find the elliptic case very hard to talk about because it's not all that technical, but it involves a lot of sort of disparate ideas. But maybe this is a good introduction to the elliptic case. So this talk today is joint with Francis Brown. And it builds on work of one, Francis himself, and two, work I've done with plus Makoto Matsumoto, that we've been writing for about 7 years, but I promise to have it on the archive by the end of the year. I have a complete draft. So, yeah, so the starting point of today's talk is this, that let's suppose we have a curve, that we have a curve C over Q, and it's hyperbolic. So by this I mean that C is going to be some smooth projective curve minus S, which is finite. So this is projective. And you have that the Euler characteristic of C is negative. So if this had genus G, you have 2G minus 2 plus the number of points in S is greater than 0. So I'm counting the number of points in S geometrically. So and so let's take a base X to be a base point. So X a base point. So either X is, say, a Q-rational point of C, or X can be a tangent vector at some point of S. Or this is a so I can use, we're going to need to use tangential base points. So but for a start, I'll just assume the base points in the curve. So we have the étale fundamental group, or the geometric étale fundamental group. This will be pi1 of the étale fundamental group of C tensor Q bar with base point X. And we also have the topological base point fundamental group, which is pi1 top of, say, the associated analytic curve with this base point. Maybe I should put bar or something on that. And we have two representations. We have a representation of the Galois group, maybe I'll call it rho arithmetic, which takes the Galois group of Q bar over Q. So this is into the automorphisms of pi étale. And we also have what I'll call rho top, which takes the mapping class group. So I can take, so in the case of a separate base point, this is the mapping class group, and it will map into the automorphisms of pi top. And one thing I should have set up here is that it's standard that pi étale is equal to the profinite completion of pi top. All right? So maybe I'll put this over here. Oh, yeah. And so what is this here? This is the mapping class group of a genus G surface, a compact genus G surface with n+1 mark points. So this, if you like, this is pi 1 of mgn+1. It's just the fundamental group of this with the appropriate base point. And so it's a mapping class group. And so I'd like to call these the arithmetic automorphisms, and these are the geometric automorphisms. And so what's the relationship? Well, the first fact is easy, and I'll explain why in a second, is that the image of Rho et al. Normalizes, and I'll be a little sloppy. I should say I will say the closure of, but I'll of rho top. And a quick reason for this is you can assemble the two representations into a representation of pi 1 of mg.
Is it quite slightly larger?
Sorry?
Can you write larger?
Yeah. Just yell at me if I write too small. All right? So, and the reason here, there's a very standard reason, is that you have an action, you have a map of pi 1 of mgn+1 over q. You have the base point, which is basically the curve C, and the base point, this maps into the automorphisms of pi, let's say pi et al. I mean, we'll treat them as the same, and this and both of these representations live in here. The mapping class group is the profinite completion of the image of the geometric fundamental group, and this base point is a rational base point, so it gives you a map of GQ into here. And the geometric the geometric part of pi 1 is normalized by the action of the Galois group. So that's saying that this guy normalizes the closure of this guy. Yeah. Okay, sorry. I usually don't have this problem. Okay. I guess I'm trying. We have, maybe don't have my glasses on. Let's see. Pi 1 of mg, the ends here are approximately correct, okay, over q. With the base point, I'll take it to be this curve, so it's really the closure of the curve count. Maybe I'll put this S union X. Right? And this guy here will map into the automorphisms of pi et al. Right? And this representation here combines both, because this is a rational point, more or less, of the moduli space. You get from, I'll call it CX, gives you a map into here, and the rest of this guy here is the closure of the mapping class group. All right. Okay, so let's let n be equal to the normalizer of the geometric stuff. Closure, right? So of the geometric automorphisms in aut pi et al. And so what we do is we have I'll just call it rho bar, which is going to take us into n mod the image of rho top bar. Is this still too small? Anyway, we have this guy here, we have this homomorphism, and for reasons I'll explain shortly, this representation is independent of the curve and the base point. And it's a silly reason. One way to think about this is that you could think, you can do this construction. So forget about the Galois group. Think just about, it's going to be clear in the Hodge theoretic situation, which I'll explain in a minute. But you can do this for every curve, and you more or less get some sort of local system of groups over the moduli space. And the fact that you've modded out by the geometric automorphisms makes it geometrically constant. You know, it's over the... Yeah. So if you were thinking of the Hodge theoretic analog, so the Hodge, which I'll explain in a minute, the monodromy, you know, the monodromy action of the mapping class group is going to be trivial, and you're getting a variation of Hodge structure with trivial monodromy, so you're getting a constant variation of Hodge structure. And the Galois analog is just a representation of GQ. How do I get these boards? So I'm going to mainly talk about, whoops, how do I stop that? So the problem, whoops, sneaky, hang on, stay. Okay, so the problem is to determine the image. And I don't only mean just the image up to isomorphism, I mean basically how it acts modulo geometric automorphisms as well. So, so here's an alternative. Is the font point size okay? No. Okay, so, and this is I'd say more tractable. And it's also, in a sense, more motivic because we're going to deal with pro-algebraic groups instead of with profinite groups. So we're going to let pi unipotent be equal to the unipotent, also known as the Malsev completion of, say, pi top. And I'll think of this as a pro-algebraic group over Q. And you also have if you take the unipotent completion of this, the continuous unipotent completion of this over QL, this is just equal to pi unipotent tensored with QL. Just the, right? So now basically my fundamental groups are the same. And now let me describe what this guy looks like. So we're going to let P be equal to the Lie algebra of pi unipotent. So this is a Lie algebra over Q. And in the closed case, this is the isomorphic to the free Lie algebra generated by H. So H will be H1 of the curve, H1, say, of C analytic with rational coefficients, divided out by the ideal generated by what I'll call theta. Theta will just be equal to it's the infinitesimal version of the usual relation, some aj, bj, j equals 1 to g, where aj, bj is just a symplectic basis of this guy here. And then you have to complete the whole thing, and this would be a closed ideal. So it's actually, to me, it's still a non-trivial fact that this is true, but you prove this, say, using Hodge theory.
Is there no terms involved by the filtration?
Sorry. So this is here. So here, C is projective. So I'm going to concentrate on two cases. One case where I have one puncture and I have a non-zero tangent vector here. And in this case here, P is isomorphic to the completion of the free Lie algebra on H. And the other case is the projective case where I just have a base point X. Right? And in both cases, so in the punctured case, you just get the free Lie algebra. In the complete case, you get one relation, which comes from the symplectic form. Where am I lost? All right, and so and again, we have a representation, I'll call it rho unipotent, which is going to take, well, I'll call it rho L unipotent, which is going to take GQ. It acts on the QL version, and it's going to go into the normalizer of the image of the geometric automorphisms. Yeah, the Zariski closure divided by the closure of the Zariski closure. And so I can write this as, I'll write N, so the automorphisms of I should say of P. So the automorphisms of P is a pro-algebraic group, and there'll be the Zariski closure of the mapping class group, say I'll call this GGN, is some pro-algebraic group. And if you know about relative completions, it's the image of the relative completion of the mapping class group inside this, the automorphisms of P. And so the problem is to determine, so the problem that I want to address is determine the image of, and maybe I put an L here, determine the image of rho unipotent L closure. And so there is a Hodge analog. In fact, it makes sense for every curve. So P, this Lie algebra up there, has a mixed Hodge structure. And now you can look at the automorphisms of P, or let me just do it infinitesimally. Let me look at the derivations of P. And inside here, I can look at the, well, this will contain the Lie algebra of G, so the Lie algebra of G, say Gn. And this, maybe I'll call GGN. And so this is the image, the Lie algebra of the image, the Zariski closure of the image of the mapping class group in here. And you can, in between these, you'll have the normalizer. So I'll just call it N. So this will be contained in here. And we can look at N mod G. And this guy here will have a mixed Hodge structure. And so it's going to be So if you regard the category of mixed Hodge structures as a Tannakian category, which it is, you'll have a representation of pi1 of mixed Hodge structures into this guy here. And that's the analog of this guy up here. And so all of this is defined over Q. And this is actually what we're going to try to understand. We'll understand both at the same time by understanding the Hodge theory. Right, so the problem is to determine the image of this. And it's going to turn out the image of this guy here is the same as the Zariski closure of the image of the Galois group, and we can say something about it. Okay, so some remarks. So the first one is that quite a while ago, Oda conjectured that the image of rho et al. Is independent of G and N. So the genus and the number of points. And I should maybe put here L. And so this is proved by, it was finished by Takao. But it was, plus there was work of,
What is rho et al?
sorry?
I'm sorry, did you define rho et al? What is
I thought I did early on. So this is the, this was the action where it should be on one of these boards. Oh, arithmetic. Sorry. So by plus Ihara, Nakamura.
as a group, they live in different groups, but
Okay, so I guess I'm talking about the image, so the image of this guy in the normalizer mod, the image of the mapping class group, wherever I wrote this guy here. Where did it go? Where is it? Yeah, this guy here, rho bar. Let me call this rho bar arith. And so it's this guy here. It's rho bar arith is independent of G and N. So Nakamura and Matsumoto. And so it's also proved, it also holds in the prounipotent case for pi un. So the analog holds for this guy here. And so what this says, so the image in both cases is determined by the 0,3 case. So this is the genus, and this is the number of punctures. And so what's the genus 3 case? It's GQ is going to map into the automorphisms of pi1 unipotent of p1 minus 0, 1 and infinity. And we take a suitable tangential base point here. There's 6 possible choices. You want an integrally defined tangent vector, so here's sort of 0, 1 and infinity, and there are the 6 integrally defined tangent vectors here. So if the parameter is x, this tangent vector, say, would be d dx. And there are no geometric automorphisms because the mapping class group gamma 0, 3 is the trivial group, so there's no geometric automorphisms. And the pro-unipotent analog is, yeah, so, yeah. Sorry, I'm in the unipotent analog situation.
The prounipotent case, you have tension with, you have done it on a Lie algebra level, right?
Sorry?
So when you
Yeah, okay, so maybe I should, sorry, I've been in, I can put this here. But the automorphisms, the group and the Lie algebra are isomorphic by the exponential map, so there's no difference.
So is it then, is then 2, is that a formal consequence of 1, or is it?
Sorry?
Is 2, is that a formal consequence of 1, or is it something that you have to...
No, I don't think it's a formal consequence of 1, but they prove 2 as well as 1. I think it also holds in the pro-L case. So, let me pick it. And so the next remark is that 3 is that, so Deligne and Goncharov they proved that, I'll just put Lie pi 1 unipotent of P1 minus 0, 1 and infinity with one of these, any one of these 6 natural tangent vectors. This guy here is an object, it's actually a pro-object of the category of mixtate motives over Z. So I'm going to say a little bit about what that means in a minute, but this means that, so this homomorphism, so have factorization. We're going to have, say, GQ here. It will map into, say, the automorphisms of Lie pi 1 unipotent of P1 minus 0, 1 and infinity with this guy here. This will, there's, again, mixtate motives form a, I'm going to leave out the Z. So these are mixtate motives over Z. I'll choose a suitable fiber functor. This guy factors through here. So this guy is a representation of the fundamental group of the category of mixtate motives. And I should here put tensored with QL. And this was tensored with QL. But this guy here is in fact defined over Q. Mm-hmm. And so we have this representation here, and you can ask, how faithful is this? So the last statement is that Brown proved that pi 1 of mixtate motives into the automorphisms of Lie pi 1 unipotent of P1 minus 0, 1 and infinity with one of these standard base points is injective. So we actually know what the image is, but we don't, actually the image of this is not properly understood. So I want to say more about this. And I should say, if you want to do Hodge theory, so here I've got tensored with QL, but this guy's defined over Q, and if you want to understand this is a mixed Hodge structure, the map from pi 1 of mixed Hodge structures into here would factors through here, because every mixtate motive has a mixed Hodge structure, has a Hodge realization. So to understand the Hodge or the Galois situations, they're both described by this homomorphism here, and so this homomorphism is Zariski dense, so this proves the Zariski closure of basically the Mumford-Tate group and the Zariski closure of the Galois action are exactly the same. So anyway, the question is, try to compute this map here and the corresponding map in higher genus. And so the way to do that, at least for me and for Francis, is not to use Galois theory, but it's to use Hodge theory. So that's somehow the point, and the Hodge theory you do in genus 1. So I'll just say a few words about mixtape motives. So MTMZ is a Tanakian category. And the simple objects, it's a Q-linear Tanakian category. The simple objects are Qn, where n is in Z. And if you tensor two of these together, you get, say, Qn and Qm together, you get Qn plus m. And the Hodge realization, I'll be brief, is just the one-dimensional Hodge structure of type minus n minus n. And the Galois realization, or the Ital realization, is just the one-dimensional representation given by the cyclotomic character to the nth power. And so, and the X groups in here are supposed to be described by the K theory of the integers. I won't say what it is. What I will say that's important is that, sorry?
Find a simple object from Zn.
Well, I think Z is too hard. We're looking at Q-Hodge structures. So, so I want to make one important point here. One thing you get from, say, Hodge theory or from the theory of motives is that if you have some object, and I'm going to drop the Z now, the significance of the Z is that they're representations, for example, of the Galois group over Q, of Q bar over Q, and for every L they're ramified at all primes away from L, for example. So anyway, if you have such a guy here, then you have, this guy will have a Q de Rham realization. So this is a Q de Rham realization. And this guy is naturally, there's no choice. This guy will have a Hodge filtration, and it's the direct sum of FP VDR intersected W2P VDR. But it's a rational vector space. And so this natural splitting is preserved by every morphism. And what, as is typical in Hodge theory, this lets you work with graded objects rather than filtered objects. And so you can apply this to the, say, the Lie algebra of the fundamental group of this category. And what you have is that if you look at pi 1 of MTM, it maps to GM. And basically, and there's some pro-unipotent kernel. This is pro-unipotent. And this guy has a canonical splitting, and if you think about it, comes from this here. If you took, to be technical, if you take the de Rham fiber functor, the Q de Rham fiber functor, you get a canonical splitting. That says this guy here is a representation of Q. So if you let K be equal to the Lie algebra of K, so K will be equal to the completion. It'll be just the product of the graded quotients of, yeah, let me write it like this. You just take the associated graded of K and you complete it. And this is a natural isomorphism. If you take the de Rham version of this fundamental group of mixtape motives. And so what is graded K? So I'm going to be sloppy and I'm going to identify K with graded K. So I'll forget the completion. So K, when I do that, is the free Lie algebra on generators sigma 3, sigma 5, sigma 7, and I'll put sigma 9 just so you don't think they're all prime. Just this one generator for every odd integer greater than or equal to 3. This guy will be acted on by GM because of this semi-direct product here, and here this GM acts with weight 3, 5, 7, 9, and so on. So that describes the fundamental group of this category, and this was all work of Deligne and Goncharov. I mean, the shape was expected just based on predictions of the theory, but what's remarkable is you actually get, in this case, a theory of mixed-state motives with exactly the correct X groups. All right, so what... So incidentally, because the normalizer modulo this group, in the unipotent case is a representation of this group, it means everything inside is a mixed-state motive. All right, so the next part is Marita's conjecture. So Yuki Morita, I guess, so he's a Japanese topologist, and he talks a lot with people like Oda. And so Marita's not an arithmetic person by any means, but he made a conjecture about what the image of these sigmas are in this derivation algebra. So let me describe what it is. So here again, Cx is going to be either a closed surface. Actually, let me take, the way I'd like to draw tangential base points, take something I learned from Edward, is you take the real-oriented blow-up and you put basically the tangent vector. So you blow up the point where you were attaching the tangent vector, take the real-oriented blow-up, and the tangent vector will give you a point on the boundary. All right, so this is the case where P equals the freely actually graded P equals this guy here, or it is the closed case where you've got, here's your X here, and graded P is just going to be the freely algebra on H mod theta. And theta is the logarithm of the loop that goes around the boundary here, or of rotating the tangent vector. So let me say a little bit about the weight filtrations. So these guys carry a mixed Hodge structure or whatever category, and they carry a natural weight filtration. And the weight filtration is that W minus N of P is equal to the nth term of the lower central series of P. So this means the nth term of the lower central series. And yeah. Right, and now so we're going to without a lot of explanation, I'm going to work with the graded objects, but Hodge theory and so on allows us to do this. So der 0 LH, this is going to apply in the one boundary case. These are going to be the derivations, delta in derivations of LH, such that delta theta is equal to 0. So this is an infinitesimal analog of the mapping class group of a surface with one boundary component. And this guy is going to map to the derivations of the freely algebra on H divided by the ideal generated by theta. Any such derivation induces a derivation of the quotient. This is the analog, the sort of sum analog of the Lie algebra of the mapping class group of a closed surface. All right, so there's a basic proposition here. Right. So the weight filtrations of these Lie algebras induce weight filtrations here. So these guys have weight filtrations. And basically, to know what a derivation is, you just need to know where the generators go. The generators have weight -1, and if you get mapped down into stuff here, say the stuff that's purely of weight, say -n, would map the -1th graded quotient into this part here. That derivation would have weight -n. Anyway, so proposition here is that for all g greater than or equal to 2, there is a unique... one other comment is the symplectic group of H, SPH, acts naturally on H. It preserves theta, so it acts on this guy and it acts on this guy. So there's a unique copy of the representation S2n plus 1H in GRW minus 2n minus 1 derivations for both of these cases for all n greater than or equal to 0. And you can see if I take n equals 0, this is just a copy of H in here. They're going to somehow, at least here, they correspond to inner derivations. So they're not interesting. The interesting ones are for n greater than or equal to 1, and these match up with, there'll be an S3, S5, S7, and so on, and they should match up with these guys. These guys here, I should say, this is spanning a copy of Q of 3, so this guy has weight -6. This guy has weight -10, and so on. And in general, Q2n plus 1 has weight -4n minus 2. Right? It spans a copy of Q2n plus 1. And so Marita looked at this guy here, and he could prove that it's not geometric. So, right. So this is actually not hard. This is a sort of exercise in representation theory. And Marita is that each S2n plus 1H is not geometric. N greater than or equal to 1. So for the S3, S5, S7, and so on. And then he made, so then, okay, so the answer for you is I have the relative completion. Well, let's just do it this way. I take, what does it mean to not be geometric? I have the mapping class group. Okay, to be purely accurate, I'm identifying P as isomorphic to graded weight dot P, right? So I do that. And so then I have a map from, say, gamma, just in the closed surface case here, into the automorphisms of, say, P. And I can take the Zariski closure of the image, and I can take its Lie algebra. And so this will have a semi-simple part, which is going to be the symplectic group, and there's a unipotent part. And I ask if, in the Lie algebra of the unipotent part, this guy appears. Or another way to say it is if I look at the image of the relative completion in here, and I look at, and so on, and I just ask if the image of the Lie algebra in here after I take graded quotients is a representation of this guy, and I ask if that's in there, right? So, yeah, sorry, I a bit vague sometimes because I want to avoid all the terminology of this other stuff. But anyway, this guy's not geometric. So it's not coming from the Zariski closure of some element of the mapping class group. All right, so, and the Galois image that we know lies outside the geometric image. We already know it's large out there. So what we can do, so what Marita said, okay, let's take these derivations here. They're of, we can take the bracket here, S2n plus 1h, and we can map this into the stuff graded weight minus 4n minus 2 of, say, the derivations, say, derivation 0 LH, and this guy will map into all right, and in here, so this is a sort of an odd representation of the symplectic group. I can take the symplectic invariance. This is an irreducible representation, so this guy's just isomorphic to Q. In fact, as a Hodge structure, it's a copy of Q 2n plus 1. And so Marita's conjecture was, or is, that so we've got the image of these guys. We also have, we've got K, if we like, we've got this map sigma 3, sigma 5, and so on. This is mapping into, so the I'll just, on the level of Lie algebras, it's the normalizer of the geometric modulo the geometric. And so this is sitting inside the derivations modulo the geometric stuff. And we've also got these, and I'll call this guy here, pick a suitable generator, I'll call this guy here mu 2n plus 1 squared. So by that I mean pick a generator here, and I'll call the image of that generator this guy. It'll be a derivation here. So we've also got these mu 2n plus 1 squareds in here. And this guy turns out to be a trivial representation of the symplectic group. It's basically because the symplectic Lie algebra is in here. And so Marita conjectured that sigma 2n plus 1 is proportional to mu 2n plus 1 squared. I mean, it's a very, I don't want to put it down. It's actually a very interesting conjecture, but it's too naive probably to be true. And the reason is because if this were true, this would give canonical generators of this Lie algebra, but they're not, it would rigidify them. But up to weight, they're natural, but you could always replace sigma 11 by sigma 11 plus, say, for example, sigma 3, sigma 3, sigma 5. The generators are just not known to be canonical of this Lie algebra. And so, and if Marita's conjecture were true, it would imply that, and that would be a very sort of remarkable thing. But you can ask if it's true to low order. And so that's what we've proved. So I guess I've got 9 minutes. Right, and there are various issues here too. So you could have complained that how can I talk about K acting if C is a smooth curve, because H1 of a smooth curve is not of type PP, it's not Mixtape. So let me just race a little bit here. So there's a technical issue, is that, that H1 of a smooth curve is not Tate, not Mixtape. It's not of type PP. But what is true is if you degenerate a curve, and so if your vanishing cycles span a maximal isotropic subspace of the first homology, then the limit mixed Hodge structure on H1 is Tate. It'll be a whole bunch of copies of Q and a whole bunch of G copies of Q and G copies of Q of 1. Right? So I'm going to exploit this. And because of this, I'm going to talk very briefly about Ihara curves. This is not an official name yet, so you can complain to me, suggest a better one. But there's a Tate curve in genus 1, and there are Mumford curves. Mumford curves are too general. And let me just say very quickly, the point is if you have an Ihara curve, it's a theorem that Francis and I proved that the unipotent completion of its pi1 is a Mixtape motive. but it's a genus G curve with this property. All right? So what's an Ihara curve? Well, you take, very briefly it's this. You take, suppose you want a curve which is quote-unquote smooth, but whose say homology is Mixtape. What you can do is you can take a maximal degeneration. So here, do that. So you take a Pants decomposition and you degenerate that. So you've divided it into what the Japanese like to call tripods, just these little pairs of pants. And actually maybe you want to add a base point. So I'll also have one piece that's shaped like this, right? So think of this as a P1 minus 0 and infinity, but you've really got, it's a P1 with 3 tangent vectors, right? And so this is sort of Grothendieck's Lego Teichmüller. You're taking pieces, and each, if this is a P1 with a real-oriented blow-up at each one, you've got 2 tangent vectors at each cusp. So there they are. You've got these pieces. You give them to your kid and you say, build me a genus 3 surface. So you're not allowing arbitrary Dane twists. You've got to match up the marks. So you can either attach them this way or that way. Anyway, so you've got one of these. So one way to think about it is if you're in the moduli space, so M bar G1, say, and you're at these curves occur, the singular curves occur at the 0-dimensional strata of the boundary. They're copies of spec Z. And then, so if you're in genus 1, there's the modular curve and you've got Q equals 0, and over it you've got the nodal cubic, and then there's this Tate curve which is defined over Z of power series in Q, which is a sort of smoothing of this guy, right? So what Ihara and Nakamura did is showed is that if you have any maximally degenerate curve, so any curve corresponding to this point here, you can spread it out over ZQ1, Qn for the appropriate n, whatever the dimension of the moduli space is. And so you should think of this guy I just described as the fiber. There'll be a whole bunch of integral tangent vectors here. If you want to deform a node, you have to take 2 tangent vectors, right, and spread them out. So basically what you're doing is you're taking when you attach these guys, you're taking the tensor product of 2 nodes, and it's giving you a first order deformation. So that's giving you a whole bunch of tangent vectors here, integrally defined tangent vectors.
Does it mean that you sort of assume that half of the functional Newton coordinates vanish? Or, I mean, you don't give the universal family here, right?
Yeah, this will be the universal, sort of formally the universal family here, but it's defined over Z. That's the point. You want this game, you've got to make things defined over Z, and you've got to ensure that they behave well mod P for all P. But that's what Ihara and Nakamura did. And so what I want to say is if I want to talk about the Hodge theory of such a curve, what is it? It's the limit mixed Hodge structure associated to this tangent vector. So I mean, these are necessary but technical but necessary points. Well, the way I wrote in my notes, 3G minus 2. Well, it depends on, I didn't want to get too much into that because the n's different for the tangent vector and the other one. But it's roughly 3G minus 3. All right, so the whole point is that this local system, which I'm now, so you've got this normalizer of the geometric stuff, modulo the geometric stuff. You can think of this as a local system over mg whatever, mg1, and think of it Hodge theoretically, it's got no geometric monodromy. It's a constant variation of Hodge structure, so you can push it over the boundary. But these guys themselves, the n and the g are changing, but the quotient is not changing, it's constant. And so to try to prove Marita, you can use degeneration. So maybe I should just state the theorem. Yeah. I need to define a filtration. So anyway, the idea is we're going to use is degenerate. We're not going to quite degenerate. We're going to go out to this sort of first order deformation of, so these things we're calling Ihara curves, degenerate to Ihara curve. And I should say there's a theorem in here. This is with Francis. Is that P of, say, an Ihara curve is in MTMZ. So this means we don't have to work with the Galois group. The Hodge theory is relatively simple, and we can sort of glue things together in a way we hopefully understand. So the next thing I need to describe is the Q filtration to state the theorem. So we only proved Marita to first order. So what does first order mean? Well, we have P. I want to define a filtration. So I'm going to take P, and it will be Q0 of P. And Q1 of P is just the commutator subalgebra. But then what we're going to do is go down the lower central series of the commutator subalgebra. So we'll go down here to say Qm of P, and this is going to be the mth term of the lower central series of PP. Okay. And so I'll try. So let me at least just state the theorem. So the theorem is for each g greater than or equal to 2 and each n greater than or equal to 1, there is a non-zero, there's C2n plus 1 in Q cross such that sigma 2n plus 1 goes to C2n plus 1 mu squared 2n plus 1. So Marita would conjecture they're equal. So mod Q3. So what do I mean? You've got n over the geometric, and now we're going to map this into, we're going to take this n over, we're basically going to look inside the derivations of P modulo Q3P. So just take the analog of this inside here. And so this is the lowest order you expect to see anything. So the leading term of this Galois action is given by the square of this Marita class. And so I'll say one word about the proof. I've got -1 minute, so one word about the proof is that the only place where we really understand the Galois action is genus 1. So we know everything is independent of the genus, and there's some lucky accidents in representation theory saying that there's a unique trivial representation mod Q3 where you'd want it. And so we know that the sigma has to go there, possibly to 0, and we know the mu squared has to go there, possibly to 0. But we can prove non-triviality in genus 1, and genus 1 we understand. So basically, you take an Ihara curve where at one end you've got this and you've got other junk here. We know the Galois action is diagonal, so we sort of can specialize to this half here. And in there, it turns out that you so one thing that Francis is good at that I'm bad is taking computing explicitly the periods of twice iterated integrals of Eisenstein series. And knowing those periods is enough to determine this up here. So to determine the low order terms of the action of the sigmas. So that's, I'll stop there.
Are there any questions?
I'm not sure whether I understood.
Oh, it's on, huh?
He's got a loud voice.
I can ask the question. Does it mean that I think these sigma, alt sigmas, right? They sort of parameterize state extensions. Is that correct?
They determine extensions. So this one determines the extension. If you're looking, say, at the Hodge realization, if you're looking at the extension of, say, Q by Q of 3, then this guy would correspond to the extension given by zeta 3. This one corresponds to the one given by zeta 5, and so on.
So does that result tell you that these are realized in a canonical fashion involving this representation of the symplectic group?
Yeah, already the injectivity, which applies to any curve, even over the complex numbers, tells you that every multi-zeta appears in the periods of its mixed Hodge structure. Because the mixed Hodge structure on its unipotent fundamental group, because those periods determine the periods of the derivation algebra, and therefore of any subquotient. And then the subquotient of the normalizer modulo geometric is a Mixtape motive, even for any complex curve, which is sort of bizarre. And so, and then Brown's theorem says that that Mixtape motive generates the category of Mixtape motives because the representation of K is injective.
Are there any other questions?
How about polylogarithms?
Sorry?
How about polylogarithms?
Well, so polylogarithms of functions, when you say on P1, when you say take paths from 0 to x, so they're periods of the path torsor from x to some point, but then they're not Mixtape motives over z unless you're going from one of these tangent vectors to another. In the elliptic case, there are all these people like Enrique studying elliptic, some sort of, well, there are Bailenson and Levin's elliptic polylogarithms, but I'd sort of call them elliptic logarithms. And they also correspond to H1 of this guy here. So if you look at representations of K that vanish on the commutator subalgebra, they're elliptic polylogarithms. But there are things that correspond, periods of things that involve bigger brackets. Actually, sorry, take that back. I was thinking of another Lie. There's another Lie algebra that's analogous to this generated by things corresponding to Eisenstein series. And those things correspond to elliptic polylogarithms. And these are the sort of things studied by Enriquez. But I don't know much about them. It's not clear to me what the correct definitions are.
I suggest that we keep other questions for the break, which will be 5 minutes.
Oh, sorry.
Let's thank the speaker again.